Okay, so here in video 6, we are starting our conversation on limiting reagent or limiting reactant. And then this concept of limiting reactant will be videos 6 and 7, and percent yield is video 8. And then we will be actually done with chapter 12. So the concept of a limiting reactant or limiting reagent, we've sort of talked about before. The idea that in every chemical reaction, there are multiple reactants. The reaction stops when one gets used up. So I have some examples here that have nothing to do with chemistry that we can just think of. We already know the recipe for cars, right? That we would take one body and 4 tires, and that makes 1 car, right? And so if I have 8 cars and 48 tires, how many complete cars can I make? And you do this in your head all the time. Like there's no math or anything like that that needs to happen. But in your head, you're going, well, if I have 8 car bodies, I'm going to now need 4 times 8 or 32 tires. And then you look, oh, wow, I have 48 tires. So I can make these 8 car bodies. And then how many tires will I have left over? Oh, yeah, 16. Subtract those 2. And so what we're going to be focusing on today is this idea of comparing need to have. Right? We looked at this example earlier in the chapter. This is the recipe here, our balanced chemical equation. 2 slices of bread plus 3 pieces of lunch meat plus 1 slice of cheese. How many sandwiches can I make? Right? If I have 6 slices of bread, I know I can make 3 sandwiches. How many pieces of lunch meat will I need? Well, for every 1 sandwich, I would need 3 pieces of lunch meat. So I'm going to need a total of 9 pieces of lunch meat. I have 12. So I have more than enough lunch meat. If I'm going to make 3 sandwiches, I would need 3 slices of cheese. I have 5. So therefore, my limiting reactant are the 6 slices of bread, and I will be able to make 3 sandwiches. Right? Looking at the next example here, we all know what is the balanced chemical equation for this? Well, 1 hot dog and 1 bun. Right? Here I have 5 hot dogs and I have 4 buns. So if I have 5 hot dogs, how many buns will I need? I will need 5. But I only have 4, right? So again, we're comparing need and have. Since I only have 4 hot dog buns, I can only make 4 complete hot dogs. So here's that same sort of information, but in a balanced chemical equation. So this is the synthesis of ammonia, right? And looking at the coefficients here, it says 1 molecule of nitrogen plus 3 molecules of hydrogen will produce 2 molecules of ammonia. And we can scale that up in terms of moles. So what happens before the reaction? Well, I would have 2 molecules of nitrogen and 3 molecules of hydrogen and no molecules of NH3. Then as this reaction takes place, if I use up the 3 molecules of hydrogen, look at that coefficient, I will also use up 1 molecule of nitrogen and I will create, do you see where these numbers are coming from? These are the coefficients here. And I will create 2 molecules of NH3, which means after the reaction is over, 2 minus 1, I'm going to have some nitrogen left over. Okay, you guys know we're going to do these reactions in terms of grams though. So we're going to have to face that. Okay, so we'll start by doing this with sort of pictures like we just did with the nitrogen example. And so we're going to be using these BCA charts at first in order to get like a graphic organizer of what's going on. So here are the chemicals before the reaction, right? And so the hydrogen are the white guy. And so there are, it tells us right here, 6, right? 6 molecules or 6 moles of hydrogen gas and 4 chlorine. And how many HCl? Well, 0. And then I figure out, well, how many are going to be used up? Notice that these have a coefficient of 1 and 1. So that means for every 1 molecule of chlorine that gets used, 1 molecule of hydrogen will also get used. So which one will run out first? Well, the one with the lower number of molecules. I will use up all 4 molecules of chlorine. At the same time, I will always use 4 molecules of hydrogen because these guys have the same coefficient. So these two are the same. Now, what about the coefficient over here? HCl is 2. So that means I will create, because it's on the other side, it's a product, I will create twice as much HCl. So this guy goes up by 8. Again, why is that 8? Think of the coefficient of 2 being here, because for every 2 moles of HCl made, 1 mole of chlorine gas was used. Think of it as a conversion factor. So after the reaction, I should have 2 moles of H2, 0 moles of chlorine, and 8 moles of HCl, right? And if we were just doing this by looking at the pictures, we would get the same answer. Let's try this with a little bit different of a balanced chemical equation. And I think in this PDF, the starting reactants are actually on the next page, right? But on yours, it might be on the same page. So what do we have before? We have 10 molecules of hydrogen gas, and we have 7 molecules of oxygen and no water. Now we need to figure out which one will run out first. And this is where we start thinking about this need versus have and looking at the coefficients. If I use up all 10 molecules of hydrogen, how many oxygen molecules will I need to use as well? So if I'm able to do minus 10, what will happen over here? Look at the coefficients. Half. The coefficient of hydrogen is 2. The coefficient of oxygen is 1. So I will use up half as many. So this guy would be minus 5. And then I would say, can I do that? What is 7 minus 5? Well, 7 minus 5 is 2. That works. I just want to think about it the other way. What if I decided I was going to use up all 7 oxygen molecules or moles of oxygen? Well, how much hydrogen would I also need? Again, look at the coefficients. Going from oxygen to hydrogen, it's twice as many. Could I subtract 14 from 10? No, I couldn't. Right? This works. The red works. The blue doesn't work. So that's not going to happen. What's going to happen is in red. So the 10 minus 10, I will have no hydrogen left over. I will have 2 oxygen molecules left over. And now I need to think about, well, how much water will be produced? Look at the coefficients. This says for every hydrogen molecule, for every 2 hydrogen molecules that get used, 2 water molecules will be made. So if this guy was minus 10, this guy will be plus 10, right? He's an opposite sign because he's a product. So this is what I would have after. And then if you look at the pictures here, right? Yep. There's my 2 molecules of oxygen left over, right? There's no, how much hydrogen is left? None. No hydrogen molecules are left because it was all used up. Because once it gets used up, the reaction stops and it limits the amount of product forms. That's the whole idea behind the concept of a limiting reactant or limiting reagent. Right? So what is the definition of a limiting reactant? It is the reactant that runs out first. right? When it runs out first, it stops the reaction. And it limits, this is where it gets its name for, limits the amount of product formed. So, we've done a few examples with pictures and with cars and sandwiches. How are we going to figure out which one it is in a real chemical reaction? So this is a good example. Copper reacts with sulfur to form copper 1 sulfide according to the following balanced chemical equation. As you saw before, the coefficients are going to be very important. So the question says, what is the limiting reactant? Meaning, which one will run out first? Which one will run out first if 80 grams of copper reacts with 25 grams of sulfur? Now what a lot of students do is they automatically assume it's going to be sulfur. Because sulfur, I only have 25 grams of sulfur. I have a lot less sulfur. But remember, you have a lot less in terms of mass, but these guys are reacting in terms of atoms and molecules. And the coefficient says I'm going to need to use twice as much copper as I am for every sulfur. So we're not quite 100% sure that sulfur is going to run out first. We actually do need to do quite a bit of work to figure that out. And that's what this graphic here is showing. It says start, so these are like the steps here. So when you do these problems, you're going to go through these steps. Start with one of the reactants and convert from mass to moles, and then do the same thing with the other reactant. So just like in our regular stoichiometry problems, the first thing that you do is you convert them both to moles. And this gives us a little bit better of an understanding because copper is so much heavier than sulfur. Although it seems like we had over 3 times more copper than sulfur, if you look at it in terms of moles, I really don't, right? It's 0.7 versus 1.2. So I do have more copper, but not that much more copper. And then this is the second step. This is the one. Convert moles of copper to moles of sulfur. What I wind up doing is just labeling this guy reactant 1, labeling this guy reactant 2, and this is an important piece. It doesn't matter which one you decide to call reactant 1 or reactant 2. And then I convert reactant 1 to reactant 2 using the coefficients from the balanced chemical equation, BCE, coefficients from the balanced chemical equation. And then this is what we compare here. This is the big deal. We compare how many moles do I have to how many moles do I need. This is if I could use up all reactant 1. Right, needed to react with all of reactant 1. So what you're doing is you're basically figuring out, is reactant 1 the limiting reactant? And you will either get a yes or a no answer. And what I just figured out is if I use up all my copper, I will need to use 0.630 moles of sulfur. And look at how much sulfur I have. I have more than that. It's those two that I'm comparing. I need to compare moles of the same compound, right? So the needed is less than have, right? So this is have, this is needed. And if needed is less than have, then reactant 1 is my limiting reactant. Because I need less of reactant 2 than I have, which means I can use up reactant 1 and I'm going to have some reactant 2 left over. And then if this was the actual problem, usually the problem will say, well, how much copper sulfide can I make? Like it will ask us for how much of a product. So we're going to do 2 of these problems this way, and then you're going to have 2 for homework tonight. So let's go through them all here. And the second one is actually the one that is in your, if you want to see another video of it, it's the show me for the next one. So when 4 grams of silver, right, circle the do, underline the clue, 4 grams of silver reacts with 4 grams of sulfur, what mass of silver sulfide is produced? Okay, so step 1, convert both reactants to moles. So I take my 4.00 grams of silver and convert that over to moles. We've gotten really good at this. The molar mass for silver is 107.9 grams. Plug that into my calculator. I get 0.03707 moles of silver. Limiting, not limiting reactant, significant figures. This is the middle of the problem. This is actually just the very beginning of the problem. So I'm not going to worry about that too much. I'm going to just use a lot of significant figures, just in case they're close. Now, this is a different fancy word, allotrope of sulfur. This is when it's called a crown of sulfur, where there's 8 sulfur atoms all bonded together. It has a molar mass of 256.56 grams. So when I convert that, I got 0.01559, and that would be moles of S8, right? And I label them like reactant 1 and reactant 2, just to keep straight. So the first thing I convert to moles, and the second thing I do is basically I'm converting reactant 1 to reactant 2 using the coefficients from the balanced chemical equation. Right? This is what I'm doing. I'm answering the following question. If I used up all the moles of reactant 1, so if I used up all 0.03707 moles of silver, how many moles of sulfur would I also need? And according to the balanced chemical equation, look at this. This is crazy. 16 moles of silver will be used when I use 1 mole of sulfur. So what does that mean? That means 0.00231 moles of sulfur is needed to use up all my silver. So to use up all my silver, this is how much sulfur I'm going to need. This is how much sulfur I have. And think about it. If I would need to use 0.002 and I have 0.015, I have a lot more than I need. That's what step 3 is all about. Comparing the moles of reactant 2 that I have to the number of moles of reactant 2 that I need from step 2, right? So what do I have? 0.01559. What do I need? 0.00231. If the number of moles of reactant 2 that you have is greater than the number of moles of reactant 2 that is needed, then reactant 2 is in excess. That means I have more than I need. Reactant 1 is the one that's going to run out first. The opposite of having something in excess is running out of it. And then the opposite is, of course, true. That's what that last sentence is. So in this case, was needed less than half or was needed bigger than half? Which one is bigger? In this case, needed was less than half, 0.00231, 0.01559, right? Needed was less than half. Reactant 1 is the limiting reactant. What did I write was my limiting reactant? That was the silver. And from now on, I don't even think about the 4 grams of sulfur, because what I figured out is I have way more sulfur than I need. At the end of this problem, there's going to be sulfur that's left over. It's the silver that's going to run out. So now I can go back and actually answer the problem. It's just a single, now I just do a regular stoichiometry problem here. I do, it says continue with the stoichiometry problem to find the answer to the problem using the limiting reactant as the starting point. What did we decide was the limiting reactant? The silver. I go all the way back to 4.00 grams of silver because, we're not supposed to round in the middle of a problem. So 1 mole of silver, 107.9 grams of silver, according to the balanced chemical equation. 8 moles of that silver 1 sulfide, 16 moles of silver. And then, right, the question's asking how many grams, that's 247.87 grams of silver sulfide. Plug that into my calculator, right? Multiply by the top, divide by the bottom, 3 significant figures. Do my units all cancel out? I hope they do. Grams of silver, moles of silver, moles of silver, moles of silver sulfide, moles of silver sulfide. That's the unit that's left. So to 3 significant figures, I get 4.59 grams of Ag2S. the very end, you know, it's just a regular stoichiometry problem that you were doing all last week. It's all of this stuff beforehand that's new. Actually figuring out, you know, what we're figuring out is, why did I choose the 4 grams of silver here? Why didn't I do 4 grams of sulfur? And the one that I chose to go out front was the one that runs out first. So I figured converted both to moles, figured out how much sulfur I would need to react with all my silver. I had way more than that, so that means I can use up all my silver. And that's how I calculated that I should use reactant 1, the silver, as my limiting reactant. So we're gonna do number 17, and then you guys can start that homework. So number 17, the reaction between solid sodium and iron 3 oxide is one in a series of reactions that inflates an automobile airbag. What mass of solid iron is produced? So I want to know this, right? What mass of solid iron is produced when 50 grams of sodium is reacted with 50 grams of iron 3 oxide? Step number 1 is convert both of those to moles. So 50.0 grams of sodium, 22.99 is the molar mass for sodium, and that comes out to be 2.174. Right? I'm not grading significant figures here. I only grade significant figures at the end, so do not worry about it. Then I'm also going to take 50.0 grams of Fe2O3, convert that to moles, right? Those are my 2 reactants. The molar mass for that is 159.7. And this is 0.3170 moles of Fe2O3. Okay? It's not always, at this point, who has the lowest. Sometimes it is, and sometimes it isn't. You really do need to go through these 2 problems in order to figure out, like, the rest. You need to go through the rest of these steps to figure out which one is the limiting reactant. Okay, because if you look at the balanced chemical equation, the coefficients say that I'm going to need way more sodium. So I go through, so this was step 1, convert both to moles. Step 2, convert reactant 1 to reactant 2. I'm testing, can I use all 2.174 moles of sodium? Well, in order to use up all 2.174 moles of sodium, 1 mole of Fe2O3 will be used for every 6 moles of sodium. That means I'm going to need to use, in order to use up all reactant 1, I'm going to need 0.3623 moles of Fe2O3. So this is what I need, right? Over here is what I have, right? And this is what I'm comparing. I'm comparing need to have. In order to use up all of reactant 1, I'm going to need 0.36 moles of Fe2O3. I have less than that, right? In this case, need is greater than have. What does that mean? That means if I try to use up all this sodium, my Fe2O3 is going to run out first. My Fe2O3 is going to run out when I use up 0.3170 moles of it. I can't use 0.36 moles of it because I don't have 0.36 moles of it. I only have 0.31 moles of it. So now I do the stoichiometry problem, right? Starting with my limiting reactant. I decided reactant 2 is my limiting reactant, right? This is a test. Is reactant 1, right? Step 2, is reactant 1 my limiting reactant? I decided no, reactant 2 is. So I'm going to start back with 50.0 grams of Fe2O3 and then go ahead and answer the question. The question asked, how many grams of solid iron would be needed? According to the balanced chemical equation, or not would be needed, would be made. 2 moles of iron for every 1 mole of Fe2O3, right? Where does the mole over mole come from? That's the coefficients from the balanced chemical equation. 1 mole of iron is 55.85 grams. That's right from the periodic table. Multiply by the top, divide by the bottom. 3 significant figures, I get 35.0 grams of iron. Do my units cancel out? Yes, they do. Moles, moles of iron, moles of iron. That's the unit that's left. Okay, so there's 3. So look at like all the steps to these, right? You can see them listed out here. Use these examples. From this, you guys can do tonight, or like after watching this, numbers 24 and 25. If you notice, there's different ways to do these problems. This is the most common way. This is the ones that is taught in most textbooks. We're going to go through in video 7, 2 more ways to do these problems. So if this is really confusing, give this your best try. Ask questions in a Q&A session, and then we'll learn the 2 more methods for how to do these limiting reactant problems. Okay, and when you have to do the show what you know video, you can use any of these 3 methods. That's fine. Okay, so good luck. Give it a try, check your answers, and then ask questions in the Q&A.